Hi, and welcome. This presentation aims to meet one of the curriculum requirements for the Human Factors in AI course offered by Duke University through Coursera. We'll start by highlighting an opportunity to reduce food waste and then step through some challenges to influence consumer behavior in ways that reduce waste and increase profitability. Let's kick off by looking at the amount of food waste that food producers report. ReFed estimates that food producers and businesses lost $108 billion due to surplus food in 2023. Supermarkets throw away between 2.5% to 4% of their potential revenue in the form of surplus food, or about $40,000 per month. And this type of waste is a major contributor to the 16 billion pounds of food waste generated annually by food retail businesses in the United States. And as you might have guessed, the preponderance of waste comes from perishable items. In fact, perishables account for 80% of the waste, with produce leading the way at more than 40%. Prepared foods are a distant second at 20%. With this background, let's zoom in on the problem statement to underscore the waste reduction opportunity and the set of stakeholders involved. Here, the business problem is restated alongside a description of the current state. Note that perishables at risk of being discarded include both those nearing their expiration or best buy dates and certain quote-unquote ugly items. For example, smaller or irregularly shaped produce. Typically, these at-risk perishables end up in landfills. There are efforts to direct more of these items to the food insecure, also to feed animals, or to support composting and so on. But these ways of reducing waste do not typically have a net positive effect on the grocer's financial bottom line. Grocers will experience more profit and avoid certain other costs if they can better predict how much to order and persuade consumers to purchase more at-risk perishables. We're going to focus on the opportunity to reduce waste by influencing consumer behavior through their digital app experience. This highlights an important distinction between the different types of customers. At a high level, we do this by referring to either clients or consumers. Clients include financial backers like grocery chain executives. We must understand the business case and deliver on any commitments to improvements for these clients. Clients also include partners like store managers and other operations staff to help effectively support any changes to strategy. And ultimately, any strategy needs to incorporate solutions which influence consumer behavior in order to drive the growth in purchase of at-risk perishables that we're seeking. Grocery consumer segments are as varied as the populations living in the vicinity of the stores. To clarify how we're meeting the needs of our business clients and our grocery customers, we need to define clear business objectives with technical objectives. In this example, we propose piloting our waste reduction interventions to customers associated with 10 different stores. For the first 3 months of our pilot, we're assuming that a financial analysis has tied a 20% average reduction in waste to a 10% increase in revenue. Note how the technical objectives tie 20% conversion rates for existing subscribers and 40% click-through rates for new digital subscribers to the business objectives for loss reduction. Remember that conversion rates show how many consumers take the desired action to purchase an at-risk perishable, whereas click-through rates reflect the number of clicks relative to the number of times an at-risk perishable option is presented to the consumer. Importantly, we will also test the value proposition for the AI/ML-driven techniques against a simple heuristic that prompts users who have added an item to their cart to consider a directly equivalent product which is nearing its end of shelf life or would not normally be presented on the market aisles to its appearance. due to its appearance. If a particular AI-enabled technique does not distinguish itself from this heuristic, then its value should be scrutinized. Assuming the 3-month pilot is successful, we will take learnings from that effort into an expanded campaign that will span 100 stores. With the objectives now clearly defined, let's map consumer behavior through a task flow analysis. Depicted here is a simple representation of a thought pattern for anyone purchasing groceries for themselves or their household. Of course, human thought is not nearly so linear or simple. There are usually an array of motivations and questions interacting all at once. For example, values like good nutrition and good money management balanced against enjoyment of less healthy foods and time constraints. A digital solution that effectively suggests and convinces a consumer to purchase at-risk perishable items will first need to ascertain the customer's purpose in that particular moment and make it easier to accomplish that purpose more than any other current means. That means that a solution may support a user's decision-making upstream to identifying a need to purchase groceries, and perhaps even assist in those situations. For example, offering recipe suggestions based on the ingredients on hand. With the purpose established and the fuller context established, the solution would then determine whether perishables may help meet the need and if purchasing at-risk perishables are an appropriate choice. For example, it might be appropriate to buy at-risk perishable items if the food is going to be consumed fairly soon, or if there is an opportunity to freeze a large amount of perishables to be served at a party at some later date. The key takeaway here is that we'll need lots of data and efficient feedback loops in order to create a user experience that resonates and delights. Fortunately, many large grocers have invested heavily in data collection. Kroger alone collects data on 2 billion transactions across more than 62 million American households annually. Many chains have in-store tracking devices that gather granular customer behavior and preferences data and are able to even detect when a consumer decides not to purchase an item. All of this data and behavior tracking have ushered in the age of hyper-personalization, where AI models develop a deeper level of customer segmentation to ensure messaging and offers are better aligned with what the customer values. Many hyper-personalization initiatives attempt to identify consumer motivations and influence their choices in real time. Instead of segmenting customers solely by demographics, hyper-personalization involves segmenting by behaviors, preferences, and even psychographics, such as values or motivations. For example, apps may predict which ingredients a shopper needs to complete a recipe as they place the first 1 or 2 items in their shopping carts based on prior shopping patterns or recent internet browsing history. Likewise, grocers are trialing dynamic coupon offers to influence a purchasing decision. This framing of the business problem within the existing digital solutioning context leads us to a more refined question. Is it possible for grocers to leverage hyper-personalization to reduce food waste in their stores to improve profits through greater alignment to consumer needs? Where are the win-wins? For example, are certain users more motivated to save money or support the environment when considering the purchase of at-risk perishables? Is there a particular context that causes these motives to vary? For example, shopping on the weekend versus during a weekday evening. With hyperpersonalization, we can explore these hypotheses about behavior by going well beyond typical persona definitions to assess individual customer behavior and adapt accordingly. Let's take a look at how we might introduce our waste reduction campaign to users. Our overall approach will be to embed the waste reduction efforts within the existing user experience. for example, within a store's web presence or loyalty app, or through a broader service platform like Instacart. As we alluded to in our user task analysis, the introduction of calls to action and/or nudges will benefit from understanding the user's purpose. So let's start there. From the app homepage, we could introduce an option to choose your own adventure or receive help from a digital assistant. This would be accessible through a button or some other small feature that takes up very little screen real estate within the existing homepage layout, but is still highly visible. Once the user selects the feature, we could present them with a list of options like the ones that appear here, or have the user type their purpose for a digital assistant to interpret. Another approach would be to leverage or enhance any existing purpose finding capabilities. These would typically rely on the user's recent application interactions, their location, previous purchasing history, and so on. Whether we explicitly ask the user for their purpose or glean it from the current context, our calls to action and nudges will be embedded within the existing browse and search capabilities. Alongside the browsing list, like Buy Again, we'll introduce a clearance category, which includes all at-risk perishables, whether they have a different appearance or are nearing the end of shelf life as determined by their appearance or best buy or expiration dates. The question now becomes how best to present calls to action and with what messaging. We'll be careful to offset the risk of annoying consumers by providing easy methods to opt out of these calls to action. For example, by providing an option to opt out within the call to action message itself and within user preferences. Regardless of the user preferences, we'll continue showing what clearance equivalence items are available through the browsing, searching, and purchasing experiences. During checkout, we'll also highlight the savings and/or waste reductions achieved by the user's selection of clearance items. And maybe we'll display the opportunity lost by not selecting clearance equivalent items. This is where our marketing and user experience experts can help course correct any A/B testing efforts through the lens of consumer psychology. Of course, this highlights the need to prototype and test, and we will take this on now with a discussion about how we can use reinforcement learning to support our assessment of calls to action and nudge performance. To focus the discussion on hyper-personalization and the use of calls to action and nudges, let's dive a little deeper into how in-app personalization may be used to increase purchasing of clearance perishables as the consumer browses, searches for, and purchases groceries. We'll compare this approach to our control heuristic, which is simply to present the option when a customer adds an equivalent perishable item to their cart. Let's say that hyper-personalization's deeper level of customer segmentation defines a particular set of customers to target: younger, bearded hipsters. The traditional way to gauge the effectiveness between our heuristic and the AI ML interventions is through A/B testing over a particular period. For example, does the presentation of leafy green vegetables on clearance as keto-friendly or great value more upstream in the customer journey result in more clicks and sales over a 2-week period? Let's say a few days into the test, you learned that most bearded consumers who purchase larger amounts of avocado are clicking through the keto-friendly promotions, and you want to expand the proportion of the audience receiving the keto-friendly message to see whether the success rate is sustained. Or you notice that bearded consumers who buy larger amounts of organic produce aren't responding to either the great value or keto-friendly message. Maybe you want to test how a eco-friendly message performs with this group, or you want to change when all the different types of message promotions are presented to bearded consumers. Or shocker, you want to test whether it matters whether there's any real distinction in consumer behavior between bearded and non-bearded men. Normally, A/B tests would remain static throughout the entire testing period. Do hyper-personalization models provide a principled and more efficient way to more quickly iterate through these different scenarios? One way to accomplish this more dynamic testing is through reinforcement learning. Specifically, we'll use a one-step reinforcement learning technique called contextual bandits. Reinforcement learning uses a feedback loop of trial and error to figure out which actions lead to the highest cumulative reward over time. The contextual bandit algorithm goes beyond just supporting dynamic allocation of testing across treatment and control groups. In addition, it references user-specific context to choose an action for a particular user in near real time. After all, as we'll likely discover, not all quote-unquote younger bearded hipsters are the same. They may not even consider themselves hipsters. The algorithm references context or features like user location, time of day, and current behavior. For example, the presence of beard-friendly food items in the cart, no crumbs allowed, to determine whether a particular treatment or promotion is working well within a particular context. Based on this context, the algorithm chooses when to present a particular leafy green vegetable on clearance as either a great value, keto-friendly, eco-friendly, or some other marketing label. The algorithm continues to capture which contextual patterns and user characteristics result in more clicks and ultimately purchases of the leafy greens that otherwise may have gone to waste. In reinforcement learning, the click-through and conversion rates represent two different types of reward. Based on how our younger bearded consumers respond, the algorithm automatically adjusts its future behavior to optimize these rewards. But we have to be careful not to be too aggressive with changing the size of the frequency of the allocations, or the inferences we draw from the data will be flawed. For example, if after a single day we change our bearded customer allocation for great value promotions from 30% to 90%, we would likely be reading too much into the trend because only a small percentage of our bearded customers would have shopped on any given day. So we must strike the right balance between exploitation, that is, presenting the best experimental condition, for example, the highest performing marketing label based on the data so far, and exploration, that being continued presentation of other experimental conditions. In our scenario, other lower performing marketing labels or marketing labels with unknown performance with a particular set of conditions or context. There are a number of strategies that allow us to do this. Here we've selected an algorithm called Epsilon Greedy. At each step, a random number between 0 and 1 is selected to determine whether to explore a new option or exploit the best known option. The number is known as the exploration rate or the epsilon value. For example, if epsilon is 0.1, there's a 10% chance the algorithm will explore a random experimental condition. For example, presenting a totally untested marketing message when consumers are in a particular location or have no items in their cart. And a 90% chance it will take the action currently believed to yield the highest reward, like a standard marketing message or no marketing at all. In reality, we might want to dynamically update our epsilon value so that it is large at the beginning of the experiment when more exploration is needed and gradually gets smaller as we collect more and more data. The best known action at any given point of the learning cycle exploits the existing information and it is referred to as greedy. The greedy option is determined by the equation on the right. There are additional calculations that can be incorporated within this equation when the context X becomes highly dimensional. For example, like beard color or beard length, or male pattern baldness, or even horoscope sign. Haha. This is where the use of models allows us to share information from different contexts, and makes it possible to handle large context spaces alongside the experimental conditions. We don't go into that level of detail here, but we will review model design decisions a little more deeply when we talk about the trade-offs between model complexity, interpretability, and explainability. Let's zoom out from the details of particular algorithms and models and take a look at some AI-specific considerations that focus on how reinforcement learning and good user interface design help users efficiently identify their grocery shopping needs in a way that builds consumer trust. The consideration categories described in the Human Factors in AI course are listed here. We'll step through those now. As we outlined previously, large grocers have invested heavily in omni-channel capabilities, and grocery consumers now routinely discover products across a number of channels, including physical stores, social media, and AI-enabled apps. Omni-channel integrates these different methods of interaction into a single system in order to produce a more seamless customer experience. Typically, unless the user is very fastidious about leveraging policy or privacy policies, omni-channel systems will contain a huge amount of data about a person's demographics, their history of actions across the different digital channels, browsers, etc., and even their physical movements throughout the day. For users who see the value in the in-app personalization experience and who have opted into the associated metrics collection, our reinforcement learning model will collect user action data in the background, and this will be largely undetectable by the user. In this way, our recommendation system, calls to action, and nudges use user behavior as a proxy for supervised learning target labels through implicit feedback loops. For new users, where we don't have a lot of historical data to draw upon, we would favor exploration of calls to action and nudge experimental conditions by setting the initial epsilon settings very high or fairly high. This has the added benefit of potentially offsetting any bias that may have become baked into the model for consumers with similar demographic characteristics. The trade-off is that we assume some risk of annoying the customer by presenting options in ways that haven't been proven to be highly effective previously. Now let's discuss the privacy considerations associated with all this data collection. We'll start with the baseline for building user trust by first aligning with privacy laws. With the patchwork of consumer privacy laws enacted by states across the U.S., we'll conform to the most stringent rules which are detailed in the California Consumer Privacy Act. Users will be asked to opt into collection of the data in order to improve their in-app personalization experiences. The full details on what data is collected and its purpose will be accessible directly through the application via customer-controlled settings. In addition, info on corporate accountability specific for CCPA compliance and contact information will be available, and the user will have ultimate control through the app to opt in or out of data collection and to update or delete any personal data. Instacart provides a good example of how to communicate privacy information to users, and a link to their privacy information page is available on this slide and appears towards the bottom. Having established data collection and user privacy measures, let's turn now to the topic of transparency into the model. With reinforcement learning, the focus for the technical teams and their sponsors often turns to discussions on its performance. For the contextual bandits algorithm we've chosen, tech teams can monitor reward optimization through measures like the ones listed here and use these to direct further model improvements. Ultimately, these types of technical model measures will be expected to translate into profitability indicators like conversion rates and customer lifetime value. Note that none of these speak to how the model actually accomplishes these measures of success. Nonetheless, it's important to start here for transparency's sake to establish how we're keeping score on the model's performance from the technical and business perspectives. The level of transparency we can technically provide will be determined largely by what's referred to as the model's interpretability. Interpretability is the ability to understand the model's internal workings from its technical design. Our selection of the Epsilon Greedy strategy is fortunate in that at this level of the model, we're talking about a straightforward heuristic that seeks to balance the trade-off between exploration of new options versus exploitation of the known best option at any given time. At this level, we could provide grocery consumers a sense of how the model works, at least generally. Interpreting how the Epsilon Greedy algorithm determines the best known action is a little more complicated, but can still be summarized or explained to grocery consumers through the summation equation we mentioned previously. But oh yeah, we can't lose sight of the fact that the context X is highly dimensional, lending itself to vector representation. We may need to summarize this concept to grocery consumers as well. What if our business sponsors suggest we should squeeze more performance out of the current model? Maybe we decide to track our precision or confidence in the Y value selected for the best known action. That's been done routinely using the upper confidence bound. Theoretically, this could provide a means to communicate uncertainty to grocery users. Or we could explore the potential for the model to perform even better by using deep reinforcement learning like DeepQ networks. But then we'd likely need to make additional technical investments like feature importance visualizations or activation maximization at each layer of the network. In our worst nightmares, the technical team would be asked to provide a clear and concise explanation of how this works to grocery consumers. So it's easy to see why technical design has to go well beyond looking at a model's performance to determine the best overall choice for a particular business and consumer context. We must balance the model's performance against its complexity, interpretability, and therefore maintainability, as well as any legal or grocery consumer expectations for explainability. This brings us on to another important question of what really matters to grocery consumers when we're talking about transparency into the model: fairness. To support fairness, we may incorporate some additional rules into the learning process, like setting higher epsilon values for underrepresented groups to encourage more exploration of experimental conditions. This can serve as a nice counterweight to any algorithms that use measures of centeredness, like averages, where those measures don't sufficiently represent the distribution of the data, or in this case, the diversity of the groups contributing to the centeredness measure. If we use upper confidence bounds rather than epsilon greedy, we can track how many times different conditions are served in different contexts. For underrepresented groups, in other words, different context, the model would be incentivized to explore more conditions because the condition levels would be lower where the data is sparse. In addition to these preventative measures, we should incorporate bias auditing. Here we can keep things simple by measuring click-through rates of diverse demographic groups, but typically technical teams implement measures like regret tracking and offline policy evaluation. Regret tracking measures how much a system loses by not always choosing the best possible action in a given context. Lower regret indicates better performance. By monitoring regret, one can identify scenarios where the model consistently performs poorly, potentially due to underlying biases in the data or algorithms themselves. Offline policy evaluation uses historical logs to track what would have happened if a different policy had been used. For example, this can involve adjusting rewards to penalize unfair outcomes for specific demographic groups to ensure a more even benefit distribution. So we've covered a lot of technical details related to interpreting model performance and ensuring fairness. How will this actually translate to the groceries customer's user experience? Well, we would tend not to display many model details to users at all. This is a relatively low-risk situation where any unfairness related to the opportunities to purchase at-risk perishable items would not likely have significant consequences. Given that we're performing robust fairness audits, the risk would be further mitigated. Couple the risk level with the fact that in-app personalization is the norm for consumer retail, and we've got even less reason to default to a position where we provide the user with verbose info on the underlying model that most likely results in additional confusion. Instead, we'd likely provide simple info at appropriate places in the user interface. For example, a clearance item category might state that it's sorted based on prior purchasing history or items purchased most often by customers like you. Finally, we put control completely in the customer's hands. If the clearance promotions are unwanted, the user can simply opt out of those and specify that they don't want to see separate categories for these items while browsing the interface. This concludes my response to the project for the Human Factors in AI course. Thank you for taking time to review my presentation. Reviewers, please feel free to email me if you have any questions.